All right, so today we'll kind of go over some hypothesis testing problems. Wednesday, I'll probably start going through some of those problems in the practice exams. So you start looking at those or start working through those, and you have specific questions. Bringing those to class, kind of the next few classes will be kind of most beneficial for you, because that way I'll be going over problems that you actually are having some difficulty with, as opposed to just kind of sitting through problems you might already feel pretty comfortable with, right? So as you work through those, start to identify questions you have, or any questions on any kind of old, homework or any old things that examples that we went through in class. Really, the next week or so is going to just be review, right? Really trying to prepare for this second exam. So, with that in mind, I didn't post a new set of lecture slides because I'm going to be working off the end of the ones I posted last week. So I might actually get on Canvas after class and update this just so it says like lectures 11/12, because we'll be using the end of last week's lectures this week as well. Okay. So I'm going to skip this, or no, actually, I'm going to do this, this one right here. So question 2. Okay. So we're going to use question 2 today, and then kind of start with this problem 1 up here. All right. So if for some reason we had an example I gave you like this, where you're not given the sample proportion, you're kind of given this X and N. Now, in a more formal problem, it would be set up as like, I don't know, 36 people responded this way on the survey out of 109, right? So you kind of have the number of people who responded the certain way and how many total people you have. So if that's ever the case, right, where you're just given kind of X and N, and you want to find your sample proportion, we're really just going to take, it was 36 out of 109. So you'll simply take 36 divided by 109 to get your sample proportion. So here that ends up being about 0.33. Excuse me. So that was our sample proportion that we found from our data. We have this null alternative hypothesis that were given to us, which is that, maybe we could think about this. I don't know, this was the number of people who own guns. And we wanted to know, do less than 45% of Americans own guns? We'll assume the opposite is true, which is that greater than or equal to, and I said 45% here, right? A proportion of 0.45. So we'll assume the opposite is true, which is that it's greater than or equal to 0.45, okay? So what type of tailed test do we have here? We look at the alternative hypothesis. So we have a less than sign in the alternative hypothesis. Yeah, it means we have a less than or left-tailed test, okay? And we're assuming kind of that cutoff value that we're looking at is 0.45. Okay? So we've got that sample proportion of 0.33 that we had calculated. So what we're really thinking about is we have this distribution of sample proportions, and we're going to assume it's centered around that assumed true population proportion, right? Or the distribution of sample proportion should be centered around that value if it in fact was true. We found this sample proportion of 0.33. If we're doing this left-tailed test, we do the p-value approach. The area to the left of that is our p-value, right? Because it's the probability that we saw something this far away from the assumed true value or anything further that went against the null hypothesis. So we have a normal distribution that doesn't help us if we want to find that probability. So the next step is to turn that into a test statistic, or if it's coming from a standard normal distribution, turn that into our t-statistic. Right? Once we have that, we can look it up on the table, on that standard normal distribution table, and it will tell us what the area to the left is, right? Or the probability of seeing that z-value or anything lower. So how do we find that z-value? So this is where we have an equation, and this will be in the formula sheet. It's in that practice materials folder for the next exam. You take your sample proportion, subtract the assumed true proportion. We then divide by the assumed true proportion times 1 minus the assumed true proportion over our sample size. And all of this here is in the square root.
So the square over p is what we're trying to find the z-score of.
For our sample proportion that we found.
Yeah, and then that's the assumed.
This is our assumed true proportion.
And then all of that together makes up the variance?
Yeah, so this guy right here in the denominator represents the standard deviation of our sample proportions.
Okay.
Yep, because we took the square root, right? So you're right, it's a variance, but we took the square root. Yep, so it's our standard deviation. So we've got everything we need, right? This is 0.33, this is 0.45, which will get plugged in here as well. Sample size of 109. We could, plug in our numbers and enter this into our calculator, right? So I work along with you because I forget exactly what this one is. Divided by the square root of 0.45. So negative 2.52 approximately. All right, so if we plug our numbers into that test statistic equation, we should get a test statistic of about negative 2.52. We round to the second decimal. Okay? So if we're using the p-value approach, we want to find what's the probability I saw that test statistic or anything below it. We go to those standard normal distribution tables. And so we had negative 2.52. So the area to the left of that is 0.0059. Right? So negative 2.52. The area to the left is 0.0059, which is exactly what I wanted, right? So with a left-tailed test, it's pretty easy, right? Because once I go to the table, that's exactly the area I wanted. If it was a right-tailed test, I could look up the value, but then I have to subtract from 1. Right? So I've got my p-value now, right? Where can I write this? So let's say, I'm going to erase this here for a second. We don't really need this side of the distribution anyways. So to make our rejection decision, we only reject if that p-value is less than alpha, right? Well, we have alphas of 0.1, 0.05, and 0.01. Here, our p-value is 0.059. Is that less than 0.1? Sure is. So we could say that we reject at that 10% significance level. Is it less than 0.05? Sure is. So we can reject at the 5% significance level. Is it less than 0.01? It sure is. So we can reject at every single significance level here of our kind of 3 typical benchmark significant values or significance levels. So using the p-value approach here, I think this one is pretty easy. Once you hit that really small p-value, you just check to see, is it less than this alpha? Now, you might be specified one specific, right? You might be asked, is it, can you reject at the 5% significance level? Well, then you would be using an alpha of 0.05. But once you have the p-value, it's pretty easy to check against all 3 pretty quick, okay? Excuse me. Any questions on that before I keep moving? Kind of erase this here in a second, so let me know if you have any questions. Good? All right, so if instead of using this p-value approach, which if we were kind of going forward, let's remember, we rejected at every single level. I wanted to instead do the critical value approach. I'm dealing with a proportion, so I can use that standard normal distribution. I want to find the critical value that gives me alpha in that tail. Okay? Let's assume we'll look at the first alpha, which is 0.1. Okay? So we're going to look at an alpha at the 10% level. We're going to do all 3 levels in here in a second. So I want 0.1 in that lower left tail. So I now don't have a z value, right? That's what I'm trying to find. I'm trying to find that critical value, which comes from the standard normal distribution. So it's a z value. But I know the area I want to the left of that z value. I want 0.1. So I scroll down. Looks like this is as close as I can get. So in between negative 1.28 and negative 1.29. So I'll take the higher an absolute value of the two, so negative 1.29. And that's my critical value for the 10% significance level, or an alpha of 0.1. I could then look up, okay, well, and then my rejection region, sorry, before I almost got ahead of myself. The rejection region would just be, okay, what's the probability I see something that far away from the assumed true proportion or anything further, right? So for a left-tailed test, kind of that arrow gets drawn into the left tail to make our rejection region. For right-tailed tests, it gets drawn to the right tail. Two-tailed tests, we got that pair of critical values. The arrows just kind of go into the tails there, okay? So if I wanted to look up the critical value, that gave me, say, an alpha of 0.05. I could do that as well, right? And kind of create kind of the three different significance levels. I could plot the critical values, draw the rejection regions, and then plot my test statistic to see at which levels can I reject. Well, now one quick and easy way to do this is instead of going through that process using that standard normal table, remember the t-tables, that last row gives us the standard normal distribution values, right? If we had degrees of freedom of infinity for a student t distribution, that would actually be the standard normal. So this will give us the same values that we would find using that standard normal distribution. But this kind of table is nice because it can go out to the third decimal instead of having to kind of be forced to go to the second decimal, right? Unless we wanted like a three-dimensional table with that standard normal, we couldn't get to the third decimal there, just doing it by hand. So if our alphas are 0.1, 0.05, and 0.101 that we're interested in, these three columns, we then go down 1.282, 1.645, and 2.326. We can get them all very quickly. Now, the only issue with doing this is the student t-table is always set up for the right side of the distribution. So we're dealing with a left-tailed test, so we want the left side of the distribution. But the thing is, it's a symmetric distribution, so every value that we see that was positive, the same thing would be true about the left side of the distribution, just that they would all be negative. So instead of negative 1.29, we can get even a little bit closer here, right? Negative 1.282, negative 1.645, and then what, negative 2.326, right? So we have our critical values. I'm drawing in kind of here my rejection regions. Now I can plot my test statistic and see which of these rejection regions is in, right? So if we remember, our test statistic was negative 2.52. So if I'm going to plot that, it's going to be somewhere over here, which is in the rejection region at each one of these levels, right? And remember, these correspond to the 1%, 5%, 10% significance levels, so I can reject at every single level, which is exactly what we decided when we did the p-value approach, right? So either approach, we got the same rejection decision, it's just a slightly different way of doing it, okay? Are there any questions on that before we keep moving here? All right. There's something else I wanted to say. So the next thing that I'm going to show you is, I'm going to rewrite this out for us. I'm going to leave this so we can think about it. So just so it's a little bit easier to see, I want to prove something with it. So here was our equation we had for our test statistic when we're looking at a hypothesis test for a sample proportion. Okay? So if we look at problem 2 on this slide, maybe, there we go. If I try to figure out what the sample proportion is, so 96 over 283, it's, well, I think I did this in the earlier one. Let's change this to 94. So if you do 94 over 283, you get almost the exact same sample proportion of 0.33, okay? So it would be like if we found the exact same sample proportion, but now we have a higher sample size, okay? So everything else has remained the same, We found a sample proportion of about 0.33. The only thing that's going to change now, right? We still have the same assumed true proportion. The only thing that's going to change is my sample size went up. Right? So I'll kind of try to write these steps down. So like 1, n goes up, right? What's going to happen to the standard deviation of our sample proportions, which is like this entire denominator? The sample size goes up, what happens to this fraction? Just the denominator.
It goes down.
Yeah, right? It's actually going to go down, which is what we said. If we have a lower standard deviation or a lower variance for our sample proportions, which kind of erased it, but remember that's what this distribution was for, it's going to become more peaked. So it's going to look something like this, right? So if I now think about, well, what would my p-value be? I still found that same sample proportion of 0.33, but now with this higher sample size, my p-value, much, much smaller, right? Well, why? Well, because remember, this test statistic represents the number of standard deviations away. If my standard deviation is smaller, that same distance will be a higher number of standard deviations away now, right? You can imagine like this is what we're 0.12 below it. So if my standard deviation was 0.06, I'd be 2 standard deviations below. But if my standard deviation with a higher sample size fell to 0.03, well, now I'm 4 standard deviations below. So by taking this higher sample size, it decreases the standard deviation, which kind of increases my test statistic here, or my z statistic. If my z statistic goes up, you kind of think about if the z statistic gets higher or larger, when I say it goes up, sorry, the absolute value of my z statistic gets higher, right? It gets higher in magnitude. So if I think about the p-value being the area to the left of my test statistic, well, now with a higher sample size, this test statistic is somewhere out here, my p-value is going to be much, much smaller, right? So my p-value would then be smaller, right? Which would mean what? If I only reject when the p-value is less than alpha, am I more or less likely to reject with a smaller p-value? The p-value is getting smaller. It's now going to be more likely that that p-value is less than alpha, right? So with a smaller p-value, I guess if we wanted to kind of, I'm going to write it up here out of order, but the smaller p-value, we're now more likely to reject. And really what this is all kind of, why all this can, we know this is going to occur is because we know that sample size is influencing that standard deviation of our sample statistic, right? Or the standard deviation of our sample proportion. So as that distribution changes, seeing the same sample evidence will now be a different number of standard deviations away from that assumed true value, right? So taking higher sample sizes makes it more likely we can reject certain values or kind of pinpoint down where that true population parameter lies. Okay. Any questions on that? No, it's kind of, all right. So the next one I want to go over today is, we'll skip kind of questions 3. We'll go to question 4, right? So let's consider that we have the following hypothesis test, right? So I'm going to start, which one do I want to do here? Let's change this one to having the same, well, I'll do this, right? Having the same kind of, we're having a different variance, but we're going to keep the sample size the same as we had before. So let's start with problem 1, right? We have a sample mean of 70, kind of this sample standard deviation of 6.9, and a sample size of 35. Now let's assume that we want to test for, maybe this is like the mean retirement age, whether or not it's different than 73 or not equal to 73. So we assume the opposite is true, which is that it's equal to 73. So we have a two-tailed test, right? Not equal to sign the alternative hypothesis means we have a two-tailed test. So let's draw out what this starts to look like. Okay. So one thing that we have to pay attention to is we're only given a sample variance, or sorry, a sample standard deviation here. So we're thinking about the distribution of our sample means. We assumed it was equal to 73. We found a sample mean of 70, which we might think, okay, so the probability of seeing that value that went against the null or anything that was further away from that assumed true value. But because it's a two-tailed test, seeing 70, it was equally as likely we would have seen 76 or anything above 76, right? And that evidence is equally damning against the null, right? Because now we're just assuming it's equal to 73, evidence on either side would go against the null. So we find this sample mean, we're gonna have to turn this into a test statistic, but now it's no longer a Z statistic, it's coming from a student T distribution because all we have, we don't have a population variance. All we had is the sample variance or the sample standard deviation. So our test statistical equation is going to be take that sample mean, subtract the assumed true mean, divide by the standard deviation of our sample variance over our sample size, where this denominator now kind of still represents the standard deviation of our sample means, but we kind of use notation that a little bit different that kind of, that signals that we were using a sample variance and not a population variance to calculate that, right? Which matters because now when we subtract the mean divided by the standard deviation, we won't have a Z value, we'll have a T value. It's coming from a student T distribution, which doesn't have a variance of 1, has a variance slightly higher than that. But once I find my test statistic, right, it's now a T statistic, which kind of signals that it's coming from a student T distribution, not a standard normal Z kind of tables anymore. I still go through the same process. I can find the area to the left of it using my student T tables. The only problem is now I have to remember I also have an equally sized area on the right. So whatever I find here, I have to multiply it by 2. All right, so my p-value is no longer in my tails. I have half of the p-value in each tail, right? The total area in the tails is my p-value, but it's split between 2 tails, right? So I plug my values in. I have 70 here, was the sample mean I found, 73, the assumed true mean, 35 was my sample size. Now I have to be careful here. I don't just plug 6.9 in. I have the standard deviation. I need to plug the variance in here. So 6.9 squared, right? So I have to be careful when I'm plugging that in. If I'm only given that standard deviation, I have to make sure I square it, right? So if we do that, we get negative 2.57. So our test statistic, if we plug those values in, it's negative 2.57, okay? So I go to my student T tables, and I'm gonna run into 2 problems. The first is there's no negative values on here, right? But we said that's okay, because we could really just create this exact same table, and instead of thinking about the area to the right of these positive T values, we could think about the area to the left if we made all these negative, area to the left of the negative values, right? So we'll go down. What's our degrees of freedom? Well, if our sample size is 35, our degrees of freedom will just be n minus 1, so 34. Right? Degrees of freedom is just our sample size minus 1. So I've got degrees of freedom 34. I'll do the subject for now. I'm going to have to erase it soon. But degrees of freedom 34 and a test statistic of negative 2.57. So I go down here. Degrees of freedom 34. Well, my test statistic isn't up here, right? I don't see a 2.57. Right? But I know 2.57 is in between these two values. And the area to the left of negative 2.44 would be 0.01. And the area to the left of negative 2.728 would be 0.005. So I know the area to the left of negative 2.57 is somewhere in between those two. So all I can do is put a bound on my p-value, or not my p-value, sorry. I can only put a bound on that one area, that one, on the left tail. It's in between 0.005 and 0.01. So visually what I'm thinking about here is I just found, I'm going to write this and I'm going to get out of the way. 0.01, right? I found that this area is in between 0.005 and 0.001, which means this area over here is bounded by the same thing. Now the problem is, what do these areas represent? Just half of my p-value. So if I want to know what my total p-value is bounded by, I still follow the same procedure, which is just multiply by 2, but now I have to just multiply my kind of lower and upper bound on that p-value by 2. So it'll become 0.01. My p-value is above that, but less than 0.02, right? So you find out kind of what one of those tails is bounded by. You then just multiply those bounds by 2, and you now know your p-value is somewhere in between 0.01 and 0.02. Okay? Any questions on that? I know we went through an example kind of quick last week, but it was a little bit easier. I think we just had where it was less than 0.005. But yeah, this is kind of tricky, right? Because for any degrees of freedom, there's only 6 possible test statistics that we could find, right? So sometimes we're going to have to bound it. Right? Now, if you were simply asked to do a hypothesis test, instead of finding this p-value, we could use the critical value approach. But before we do that, which levels of confidence can I reject the null here? So if I think about, or level of significance, I probably should say. So my alphas are 0.01, 0.05, and 0.01 that I want to test against. Right? So if my p-value is somewhere above 0.01 but below 0.02, can I reject at the 10% significance level? Well, I only reject if my p-value is less than alpha, right? So would my p-value be less than 0.1? Well, it's less than 0.02, so yeah, right? It's definitely less, so I can reject there. Is it less than 0.05? Well, it's less than 0.02, so yes. What about 0.01? Well, I know it has to be greater than 0.01, so no, and I would fail to reject there, right? So I can reject that assumed true value of 73 based off the sample evidence I found at the 10 and 5% significance levels, but not at the 1%, okay? Any questions on that before we keep moving? All right, so what if I instead want to do the critical value approach? What I would have done is, I'm still looking at that student t-distribution. The first one I'm going to find is, well, I have a two-tailed test. So I'm going to have, should have drawn these as dashed lines, hold on. So I'm going to have a pair of critical values that gives me alpha total in the tails, right? However, you can kind of think about each tail is only going to have alpha over 2 in it. Right? So let's just look up the 10% significance level. So alpha is 0.1. Alpha divided by 2 would be 0.05. So let's assume that there's 0.05 kind of in each of those tails. My degrees of freedom was 34. So I go to the table. Degrees of freedom 34. Area I want in the tail is 0.05. 1.691. Okay? So 1.691 will be my critical value, but remember I have two of them. One negative and one positive. Right? My rejection regions, anything that's greater than them in absolute value, or kind of draw the arrows in our tail. Now if I plot that test statistic, which, what did we find? Was it negative 2.57? I think that's what it was. Is that right? Okay. So now if I plot that test statistic of negative 2.57, I can see that it's clearly in that rejection region, and I can reject at a 10% significance level. Okay. I could then repeat this, find the critical value at the 5% significance level, or an alpha of 0.05, not at the 1% significance level, or an alpha of 0.01, and then plot my test statistic and see is it in their rejection regions, right? So if I do that, okay, I can actually do this all at one time. If I want the alphas of 0.1, 0.05, before I switch this, and 0.01, remember, I'm going to have to divide all those alphas by 2 before I look up my critical value for a two-tailed test. So instead of 0.1, 0.05, and 0.01, I need to look up the areas of 0.05, 0.025, and then 0.005, right? Dividing each of those alphas by 2. I go to degrees of freedom of 34. The critical value pairs I'll have for those three different alphas are positive and negative 1.69, positive and negative 2.03, and positive and negative 2.72, or 2.73 if we round it, right? So I could then plot those three. We already have the first one plotted. The second one was, I already forgot what this was, 2.01 or something? 2.03 and 2.73. So 2.03, negative and positive. Draw rejection regions. Negative 2.67 or something like that. Doesn't sound right. Oh, is it? It's 2.73. You round to the second decimal there, my bad. Think about the rejection regions there would be anything to the left of that. Well, now if we plot our test statistic, here, do the video too. So all I did was plot my pairs of critical values, and I could kind of remind myself, here was the 1%, 5%, and 10% levels. Now if I plot my test statistic of negative 2.57, it's going to be somewhere in between here. And I can see it's in the rejection region at the 5% and the 10% level, but not quite at the 1% level, which is the same decisions we made using the p-value approach, right? We rejected at the 10 and 5, but not the 1% level. So no matter which way we do, we'll kind of come up with the exact same rejection decisions, okay? And you kind of see here with when we're doing a student t-distribution hypothesis test, kind of easier to find the critical values only because you don't have to put a bounds, like we had to bound the p-value. Well, here we can just look up those three values all at once, plot them, make our rejection regions, and then just plot your test statistic against them, right? I think probably with a standard normal distribution, it's a little bit easier to think about finding the p-value. It's a little bit easier of a process if you're doing it by hand. Now, if you're using Excel, either one of them, the p-value approach is pretty easy, right? We would use the t.dist function, tell it our test statistic, it would give us the area to the left, we multiply by 2, and we'd have our p-value, right? Instead of having to put bounds on it in Excel. Any questions on this before we keep going? Yeah.
So do we use the critical value approach or the p approach?
Yeah.
Based on what you give us?
So like on the exam, what it will look like is I'll probably have questions that break down this process. So one question might just simply be find the critical values. One question might simply be assume your test statistic is this, what would the p-value be? Another question might be find the test statistic, right? Now, the short answer portion, I might be a little bit more lenient and say, you know, provides sufficient work that shows the steps that justify your rejection decision, right? So you could use the p-value or the critical value approach there, as long as you kind of, show your work and show the reason why you can reject it or fail to reject it with either approach. Yeah. Okay. That's a good question. So let's think about, I'm not going to jump. I'll do number 2. Let's do number 2 next and think about this. Okay. So let's instead say I found the exact same sample variance, exact same sample size or sample standard deviation, but I found a sample mean of 76. Okay. Well, everything's going to be exactly the same. Like every other number we have is the same, except instead of 70, I found 76, right? I still have a two-tailed test, so I'll find this area, multiply it by 2. But what's going to be the test statistic for that sample evidence? Someone was trying to get in. Okay. So what's going to be my test statistic or T statistic for that sample mean of 76? It's the only thing that's going to change, right? Same sample variance, same sample size. So remember, these test statistics, they're either z-values or t-values, which both represent the number of standard deviations away that sample evidence is from the assumed true value, right, in this case. So if 70 had a test statistic of negative 2.57, that meant 70 was 2.5 standard deviations below that assumed true value of 73. So if I see 76, what should my test statistic be? So when 70 was 3 below the assumed true value, it had a test statistic of negative 2.57, which meant it was 2.57 standard deviations below that assumed true value. 76 is 3 above that assumed true mean. It's going to be the same test statistic, but positive. But notice, if I plot 2.57, it's going to be in the rejection region at the 10 and 5% level, but not the 1% as well. And if we think about why that's the case, well, we assume that the value is 73, seeing 76 or 70 is equally as far away from that being true, right? And so anytime we would see kind of something on either side, it doesn't really matter if it's above or below if we're doing a two-tailed test, right? So seeing the same distance below or the same distance above that assumed true value ends up leading to the exact same rejection decision, exact same p-values, exact same test statistics. It's just our test statistic would be positive instead of negative. But the p-value is the same. P-values aren't negative, right? The p-value will end up being the exact same. Okay. All right, so what if instead we go to step 3? So let's say we're going from 1 to 3. Now we're back to that sample mean of 70. Everything's the same except we have a higher sample standard deviation. Okay, so this is going to be similar to what we did with on the last one, thinking about how does a higher sample size influence things. So now, if I found a higher, let's say I had the same kind of sample evidence, so I still saw 70 as my sample mean, which was 3 away from 73. But if I have a higher standard deviation here, sample standard deviation, or a higher variance, so higher sample variance, what's that going to do to my standard deviation of my sample means? Right? If this goes up, then my denominator here, it goes up as well, right? So this would get higher. So a higher variance would kind of flatten out that distribution. If the denominator here is higher, what happens to my test statistic? Actually, it's lower, right? I'm dividing by a larger number. So a higher sample variance actually leads to a lower test statistic, which if I have a lower test statistic, lower in absolute value, it's going to be moving this way, which means the area to the left of it, kind of reflecting that p-value, that p-value is going to get higher, right? And this is just the idea that if the variance on the data we're sampling from just has a higher variation, it's going to be more likely that we see something far away from the mean, right? Or the assumed true mean in this case. If the p-value is higher, we would then say that we are less likely to reject, right? Because we're setting that alpha threshold, it's less likely the p-value is kind of below that now, right? So there's kind of different ways of thinking about how different aspects of this equation, like what they really represent, what they're really changing. You know, I might ask, so you could ask a question like this in the exam, you know, probably more likely something about the sample size increasing, what would happen to kind of the p-value or what would happen to the test statistic. You kind of can think about that. And you know, even if you don't, like if this is kind of a hard logic to follow, you could really just use these numbers, right? Use a higher sample size and prove this to yourself, right? Go through the full calculation, calculate the test statistic using a higher sample size, or calculate it using a higher sample variance, or you know, whatever it is that's changing, to kind of prove to yourself why it would work that way, okay? But there is kind of that intuition behind it as well. Okay, any questions on that before we keep moving on any of those? We're not going to kind of work through this one. I generally had these set up for something different, but I just thought there were some things I wanted to point out between changing sample sizes and stuff, so I thought they were good questions. I'll probably use some of them still on Wednesday's class, even though we'll start kind of looking at practice, at those two practice exam problems as well on Wednesday, but I wanted to kind of get through those two today, right? And then this is a great, so I got 99 problems but rejected the null hypothesis in one. So this is a great stats meme. We'll work through question 5, I think, instead of doing 3 and 1 next class. This will be something that looks probably more similar to the short answer question or the 2 questions short answer that you're going to see on the exam. So we'll kind of look at that on Wednesday. Before we go today, well, that's my last recorded lecture. So I wanted to kind of go back to some things that we talked about a while ago, but I think they're kind of relevant. And I promise, since the election's over tomorrow, I probably don't have to listen to any more kind of presidential polling examples anymore. But I thought this was relevant, interesting. So there's this like 270 to win, 720 to win, 270 to win. And CNN has referenced this a little bit, and people are kind of saying this is like, they're trying to put together all these different polls and kind of give you kind of the average of them, right? Well, this is great, but I was like, well, this seems interesting. Like, I wonder how they find, like, I don't know, I don't see a sample size here. So I clicked on kind of the results, and oh, that's pretty cool. They show you kind of the most recent polls and like what the kind of predicted probabilities are. And you can kind of see like Georgia's up in the air right now, right? I mean, this poll has a 3% kind of lead. This one has a 2%, but then these three all have kind of 2 or 1% leads for Trump. So, you know, what if I take the average of these? Well, I got to looking at this and I'm like, so they're reporting that the difference is 0.2% here, right? And I was kind of looking at this and I'm like, yeah, but I mean, these are all kind of predicting it to be close. And these are like, this one is a really big gap and it has a huge sample size. Shouldn't I be paying way more attention to that one? Like, shouldn't that one be weighted more? So then I got to thinking about, I wonder how they're actually calculating this. So I copied and pasted the data into Excel. And this was the numbers they reported. And when I went to Excel, I realized all they're doing is taking the mean, right? So they're treating this 1,700 sample the same as this 600 person sample. So I then went through and I kind of calculated these weighted means by multiplying the weight by the probability, add them up, divide by the sum of my weights. And actually notice, like, even though with just taking the average of those polls, it looks like there's a 0.2% differential. There's actually like almost a percentage point if we actually treat the higher surveys like as weighted higher. And then this one, I keep forgetting to save the name, but it was North Carolina. You can do the same thing, right? What's kind of interesting here, right? If we do this one also had a 2% or a 0.2% difference. And here, I think it's because I just have this formatted wrong. Right, so they were just simply taking the average. If you do the weighted average here and make this as a percent, so it's a little bit more comparable. Notice here, this one is what? Almost less than kind of a percentage point difference. But it still is a wider gap than if you kind of look at just this simply taking the average. In fact, this gap's quite a bit larger, right? I mean, this at least pushes this up to 48% as opposed to being at 47. So I just think it was an interesting way of kind of thinking about anytime you see data presented to you, this is how they don't want you to probably go as far as this page. They probably just want you to look at this and go, oh yeah, Georgia is going to go Biden from this predicted poll. If you actually grab the data, you could probably make a lot better predictions by kind of looking at those weighted averages. Also, even just thinking about, they also kind of present this as some of these don't actually, like this poll right, I don't know which one it was, maybe this is a different state, but some of them don't kind of provide third-party candidates, which is going to greatly influence your values, right? You could be cut out in some of these cases, right? 4%, you'd be cutting out 4% of the vote. If you force someone by your question to say either Biden or Trump, you're not going to have a lot of usefulness there, right? So I don't know, it's just an interesting way to think about biases that exist in kind of the types of questions you ask, but also just very simply, instead of taking an average, treating these surveys of different sizes kind of differently and weighting the ones that are a higher sample size a little bit more, which, I mean, this is like a introductory stats class. I don't know who's working for this company, but maybe they need to hire one of you guys after you get out of here. So I don't know, I just thought it was interesting, kind of relevant. I noticed that. I guess it shows what I do in my free time. But anyways, we'll do some practice exam problems on Wednesday. If you guys have any questions kind of leading into the exam over problems that we've done in the past, practice exam questions, anything related to homeworks, feel free to reach out to me. Set up a Zoom meeting, set up a time for you to meet in my office in person if you want to. Schedule it kind of during my office hours that are in the syllabus, or even outside of those. I'm pretty free this week. So as we're getting close to that second exam, this is usually in a regular semester a tough time where people start to have a hard time. I think it might be even more so. So please reach out. And no, I won't do a quiz today since we're kind of like not really doing new material. Probably if I do an online quiz, it would be after class Wednesday. But other than that, up until the exam, no online quizzes after Wednesday. All right? And Wednesdays will probably just be another kind of survey one where I'm just kind of trying to get a vibe or for where you guys are at. Yep. All right. I'll see you guys on Wednesday.